Okay, so as I was saying, we're going to find the area of the blue shaded regions bounded on the left and the right by the lines x equals a and x equals b, above by the graph y equals f of x, and below by the graph of y equals g of x. Just like we did when we first learned this, we're going to take that area and subdivide it into a finite number of rectangles. We'll find the area of each rectangle, and we sum up those areas, and that gives us a good approximation of the area under the curve. However, if we let the number of rectangles go to infinity and take the limit of that sum, we'll get the actual area under the curve. In this case, we'll get the actual area between the curves. So you can see in the first question here, as we look at this picture right there, we've got this region subdivided into rectangles. What would an expression be that represents the height of each rectangle? It's bounded above by y equals f of x and below by y equals g of x. So I'm going to write here that an expression that represents the height is the f of x sub k minus the g of x sub k. Well, remember the subscript of k just refers to the kth rectangle, some random rectangle there in the middle. And then how would I represent the area of each of these rectangles then? Area is base times height. So this would be f of x sub k minus the g of x sub k times what? What's the width of each rectangle? Delta x. So there would be an expression that represents the area of each rectangle. So now let's write a Riemann sum that represents the approximate area of each region. And so here comes our fancy schmancy sigma notation. The sum of the area of each rectangle, which is the f of x sub k minus the g of x sub k, delta x, as k goes from 1 to n. So I'm hoping this looks familiar. We're building a Riemann sum. Again, it's the sum of the areas of these rectangles. And the actual area, notice that we have an approximation sign turned into an equal sign, is going to be the limit of this sum as the number of rectangles approaches infinity. And according to Isaac Barrow, that is going to be equal to the definite integral of the quantity of f of x minus g of x dx. And so here's the definite integral that we're going to be using, men, to find the area between two curves, f of x and g of x, on the interval from a to b. So it's more integration. I mean, this was 90% of the lesson today, is understanding the integral that we're going to use to evaluate the area between two curves. So let's go down to the three examples here. Number 2, we have a, b, and c. And I wish I could zoom in here, but it's going to spill out the recording window. But you can look at it in front of you there. For each region below, draw a representative rectangle and set up the integral representing the actual area of the shaded region. The area of the shaded region. So for 2a, I'll draw a representative rectangle. And mine's going to be blue. The width of that rectangle, of course, is delta x. The height is the f of x minus g of x. And a definite integral that would represent this area would be the integral from a to b, because that's the limits of integration, the f of x minus the g of x dx. This is essentially a repeat of what we just wrote up there, the definite integral for the actual area right there. So let's move on down to, or over to 2b. Now we have some actual functions defined. And to find the area of that green shaded region, that's going to be the integral from, I'm going to come back to the limits of integration at the very end, but it's going to be the upper function, root x, minus the lower function, which is x squared, dx. And now I have to figure out what the limits of integration are going to be. And to figure out the limits of integration, we're simply going to, no, the limits of integration, that's what we're looking for. What's a, what's b? What's the lower limit? What's the upper limit? No. It's 0 and 1. And how do we get those? What are the x-coordinates of the intersection points for these two graphs? On the left, it's 0. How do you figure that out? Set square root of x equal to x squared and solve that equation. Then the endpoint on the right is where the graphs intersect a second time right here. And you can figure out the x-coordinate of that intersection by setting the equations equal to each other and solving for x. So that's something new that you guys are going to have to be doing, is finding out the limits of integration for these problems. And you're simply going to take the curves equations, find out their intersection points, and the x-coordinates of those intersection points will be our limits of integration. Okay, let's go take a look at the unique thing that's happening on the curve on the far right. And as we notice, the region there in red, for part of the region, actually I didn't draw a representative rectangle here. There we go. There's my representative rectangle. Let's go over to the graph in 2C. For part of this region, the red curve is above the blue curve, but for another part, they switch, and the blue curve is above the red curve. Any idea what this is going to mean when we set up the definite integral? Yes?
You have to put the absolute value of the whole thing.
No. Although we could do that, but if we had to do this manually, when you take the absolute value, you have to rewrite it without the absolute value bars anyway. Hi, Chihuahua. Whoops, I got that on recording. Hey. What are we going to do, Dylan?
Integral of a to b of fx minus gx for when cosine x is above sine x, and then make it into integral of a comma b and gx minus fx when it's low.
Okay, so you have the right idea, but you would want to change the limits of integration. So the suggestion here is, let's split this up into two different integrals. One that represents the region where the red graph is above the blue graph, and I drew a red representative rectangle for that region. And then the other integral would correspond to the region where the blue graph is above the red graph, and there's a blue representative rectangle there. So in this instance, the area is going to equal the integral from 0 to, now this is the cosine curve, the red curve, and we have the blue curve as the sine curve. Where do the sine and cosine curves intersect? For what value of x is cosine x equal to sine of x? Pi over 4. So the first integral is going to be 0 to pi over 4. And the integrand is going to be cosine x minus sine of x dx. And the cosine is coming first because that function is greater than the sine over that interval. Plus, and the second interval begins at, what's the lower limit? Pi over 4. And the upper limit is dictated already in this problem. It's pi over 2. And the integrand is the opposite of the integrand in the previous definite integral. So when you have a situation like this, and it's not at all uncommon that you will, when the function that is greater switches at some point or multiple times during the interval, then you have to break this up into separate integrals according to the intersection points and when the graphs switch positions. Yes, Johnny?
How do you know which is f of x and which is 2 x? Like in the first, how did you know it's cosine x minus sine x instead of being like sine x minus x?
So for the first definite integral, the reason that cosine x is showing up first is because it's the greater function on that interval. So you want the greater function minus the smaller function. And that's going to be a positive value then, won't it? Right? The height of the rectangle in red is going to be positive because the cosine value is greater than the sine value there. And then for the blue representative rectangle, we switched it to sine of x minus cosine of x because the sine values are greater than the cosine values there. So the height of that rectangle will always be expressed as a positive value there. Does that make sense, kids? And we're not going through and solving these. I'm assuming that you guys can go ahead and evaluate those because we're not done with the problem. I'm just showing you how to set up the integrals here. Okay. let's go to the next page, because if you notice, these representative rectangles that I drew and that are all in this worksheet are vertical, and the width of each rectangle is delta x. Well, sometimes it's better or even necessary to integrate with the representative rectangles being horizontal rather than vertical. In other words, we have to integrate with respect to y and not x. And so here's an example of that right here in number 3. If we were to go try and integrate this from left to right, look at what we have here. For, I don't have any x values written here, but to the left of the y-axis, I hope you see that this is only one function that's being considered here. So we would have to subtract a function from itself if we wanted to figure out the height of the rectangle, and that's going to yield 0. And if I were to, as I move from left to right here, it's still the red function being subtracted from itself. And at some point here, now the blue function gets involved, but I'd have to have a representative rectangle like right here, and then another one down there, and now things are just getting messy, So what is much more convenient to do is, rather than have these rectangles be vertical, let's just have them be horizontal. And instead of taking top function minus bottom function, we're going to take rightmost function minus leftmost function. And at least for this region here, we can see that for this entire interval, as we go vertically now, not horizontally, the blue function is to the right of the red function over that entire interval. So it is much easier to integrate with respect to y here instead of with respect to x. Is that kind of making sense here? It's really dicey if we try to go vertically in this situation. Yes, sir? Right, they're not functions, but we're going to express not y as a function of x, but x as a function of y. So that's an excellent question. Thanks for asking that, but that's how it's going to be approached. Okay, so asking the same questions here, we get, what is the length of the representative rectangle? So we already have one that's written for us. And the blue function is the x equals f of y. The red function is the x equals g of y. So the length, the width, however you wish to call it, of each representative rectangle is the f of y minus the g of y. And then what's the area of each of these rectangles? Well, it's still length times width. So it's going to be the f of y minus the g of y. And notice that the height of each rectangle is going to be delta y. This is the exact same idea with respect to x, but we're just doing everything with respect to y. So what does the Riemann sum look like for approximating the area? Here comes our summation notation. And we're going to take the sum of the quantity of f sub y minus g sub y, delta y, and we're going to let k go from 1, oops, I forgot the k, y sub k, y sub k. I forgot all the subscripts of k. Sorry about that, man. And k is going to go from 1 to n. And just as before, we've built, using summation notation, an expression that represents the Riemann sum that will approximate the area of this region shaded in green. And to write the integral now, because the integral is defined as the limit of the Riemann sum, as n goes to infinity, we will have the integral from c to d, because those are the limits of integration, of the f of y minus the g of y dy. And there represents the definite integral we will use to find the area of the curve of the green shaded region, between the red and blue functions, but we're doing it with respect to y. Notice too that the limits of integration are c and d, because y equals c is bounded below by the line y equals c, and it's bounded above by the line y equals d. So we're looking for the y values here for the limits of integration. Okay, so let's look at an example where I hope you will notice, and for example, in the AP test, this is going to be up to you. Let's say you got to find the area of that green shaded region. You have to ask yourself, do I want to do this with respect to x or with respect to y? If I start drawing representative rectangles, I hope you see the trouble you can get into when you go, oh, what if my representative rectangle is right there? Sorry, it didn't really, something's going on with my stylus. What if my representative rectangle is